Good afternoon. The topic which I'm going to discuss today is planar transmission lines. So as we know about the transmission lines which is running for kilometers of distance, and it's all high power transmission lines. And we have another set of transmission lines called as planar transmission lines, which are going to be used in the microwave circuits, like integrated circuits. So miniaturization of microwave circuits has taken place through the development of planar transmission lines. Since we have introduced the planar transmission lines, our microwave circuits size also has been brought down. They are lightweight, low profile, and the size is very small. And this geometry allows to control the characteristic impedance of the line by defining the line dimensions in a single plane and is therefore suitable for microwave integrated circuits. So there are four types of microwave transmission lines which can be used in the integrated circuits. First one is strip line, micro strip line, slot lines, coplanar strip lines. So we'll start one by one. So strip lines, before entering into the four type of transmission lines, we can see the construction of them and then we'll come back to the theory about it. So if you see the construction of the micro strip lines, it will look like this. The first one here, which I'm showing in the cursor, that is nothing but the strip line structure, and this is a micro strip line structure. The bottom is a slot line structure. The last one is a coplanar strip line structure. So this one, the first one slot line, the structure, how does it look like is, it will have a dielectric material, and inside the dielectric substrate of certain thickness, the copper conductor will be a small strip of copper conductor will be embedded. Okay, so if you see, you have a substrate, dielectric substrate material, which is only marked as dielectric, and inside the dielectric material I'm going to keep a copper small conductor, and that conductor is nothing but a signal conductor whose width length will be W, and the substrate height will be B, and this is a bottom. You have one more ground plane, which is also nothing but made up of a copper conductor or any other conductor. Okay, and if I come to the microstrip line, here you will have one basic ground conductor substrate, conductor material. Later you have one substrate, dielectric substrate, and then I have again a conductor patch material. Okay, so a patch, a ground plane, a patch and ground plane both are made up of conductors, and you have one dielectric substrate, and whose dielectric constant is mentioned as epsilon r. And when I come back to slot line, you don't have any conductor in the bottom. Instead of that, I have only a dielectric material, but in the top I have two conductor materials which is separated. Two strips of conductor materials are there. That is nothing but shown here in darker lines. And the ground, we call one as a signal conductor, other one as a ground plane here. And when I come for the coplanar, this is a very commonly now used microstrip line for many circuits. This is how does it look like is, you have a ground plane, here also a ground plane. In the middle one, we call it as a patch or a signal plane. This ground plane and signal plane all are made up of conductors only, and this is a dielectric substrate. Okay, so the construction wise, they all are differing little bit, and basically they follow a certain mode of propagation. So if I see here, there are some lines going out of this, no, some perpendicular lines are there, and then we have some curved paths also. Nothing but this is nothing but the magnetic field and the electric field distribution shown here. Okay, so electric fields are going straight up and down, whereas magnetic fields are is in the form of a circles. Similarly, in this also you have the magnetic fields formed around the conducting material, and you have the electric fields going down the substrate. Here also the same way, E and H are shown. Here also H and E are shown. Here H and E are formed in the form of a circles, and based on the way how this E and H are formed, we can say that they exhibit some kind of mode of propagation. This exhibits a mode of propagation, either it's a TE or a TEM. This is a TEM mode of propagation. This may be TE, this may be also TE. Okay, so now we'll go back to strip lines. So what is that strip line? Strip line consists of as I already told, it's a thin conducting strip of width W, which is greater than the thickness T, placed inside a low loss dielectric substrate of thickness B between the two wide ground plates. So you will be placing the small strip of conductor inside the substrate, which has on the other two ends ground planes. The propagation characteristics, if you see here, based on the electric and magnetic field orientation, which kind of propagation this is going to take us, it's a TEM mode of propagation. Okay, where most of the electric field lines are perpendicular to the center and it's parallel ground conductors and are concentrated over the width of the center conductor. This diagram already I have explained. So now when we come to type of dielectrics, what commonly we use is Teflon, polyolefin, polystyrene, etc. These lines are used over the frequency range from 100 megahertz to 30 gigahertz. And then when we come to the characteristic impedance of a strip line, having zero strip thickness can be expressed using the certain formulas. So W by B, if it is less than or equal to 0.5, then I can find the characteristic impedance Z0 using this empirical relation. If W by B is greater than 0.5, then Z0, the formula which I follow, should be different. And the K can be represented like this and K dash can be represented in this form. Okay, so these are all the empirical formulas and there is no complete derivation how these formulas are obtained. So these are all using some experimentation and some empirical relations. These formulas are derived. And again, Z0 can be obtained simplified in this form. In this, CF is nothing but the fringing capacitance in picofarads per meter, which arises due to the fringing electric field at the edges of the strip. Okay, so this is also CF can be founded with the formula given below. And when we come to a microstrip line consists of a single ground plane and a thin strip conductor on a low loss dielectric substrate above the ground plane. So, as I already told, you will have one ground plane, you have one rectangular patch. In the middle, you will be having the dielectric substrate. So, the size of the microwave solid devices are very small, in the order of 0.008 to 0.08 mm cube. Due to the absence of the top ground plate and the dielectric substrate above the strip, the electric field lines remain out since we don't have any ground plane in the top. Whereas if you see in the strip line, you have a ground plane in the top as well as in the bottom. Whereas in the case of microstrip line, we don't have a ground plane in the bottom. In the bottom, we have a ground plane. In the top, we don't have the ground plane. So the electric field lines will remain partially in air and partially in the lower dielectric substrate. So this makes a mode of propagation completely not TEM, but it's called as quasi-TEM. Due to the open structure and any presence of discontinuity, the microstrip line will radiate the electromagnetic energy. The radiation loss is proportional to the square of the frequency. The use of thin and high dielectric materials will reduce the radiation loss. Okay, so how much thin the dielectric material is chosen and how much high the dielectric value or the dielectric material constant. Okay, dielectric constant, if we have a very higher value, and the use of thin dielectric material will reduce the radiation loss of the open structure where the fields are mostly confined into the dielectric. Okay, so now how do we find certain relations, or how do we find out certain parameters for a microstrip line? In that, the first parameter is effective dielectric constant. So we don't have only the relative dielectric constant, along with it we have an effective dielectric constant, since because the electric field lines are partially lying in the air as well as in the substrate. So due to the existence of the field lines lying open in the air as well as in the substrate, we go for having one more constant term called as effective dielectric constant. So since this propagation field in the microstrip line partially in air and partially inside the dielectric substrate, we have a effective dielectric constant that is given by the formula epsilon r plus 1 by 2 plus epsilon r minus 1 by 2. This one into 1 plus 12h. This is a very common formula, and this formula holds good when W by H is less than 1. When W by H is greater than, very much greater than 1, then I have to follow the second formula given below, epsilon r plus 1 by 2 plus epsilon r minus 1 by 2 into 1 plus 12h by W whole to the power of minus 1 by 2. Now, how do I find the other parameters for a microstrip line is Z0 I can find with this formula. Again, here also the two conditions are holding good. W by H less than or equal to 1 and W by H greater than 1. And Z0 I'll go for having very much greater than one more Z0 formula is there. And how do we find the guide wavelength lambda g, that is nothing but lambda naught by root of epsilon effective. Okay, then synthesis of microstrip line. So W by H, how can I find this? Using these two formulas where A and B are the constant terms involved. A and B can be found out with all the known things, whatever we have. So when we come to the losses in the microstrip line, for any non-magnetic substrate material, two type of losses will exist. Okay, what kind of losses is? One is a dielectric loss in the substrate, the other one is a ohmic loss in the conductor and ground plane. Because the conductor microstrip a patch structure, what is in the top as well as the ground plane, both are made up of the conductor. So there will be some ohmic loss, and as well as the dielectric substrate material will introduce some dielectric loss. So how do we find alpha D? Alpha total attenuation constant alpha can be expressed as alpha D plus alpha C. Alpha D stands for dielectric constants and alpha C stands for one is because of attenuation, one attenuation due to dielectric material, other one is attenuation due to conductor material. So alpha D can be founded by alpha D by sigma D by 2 root of mu by epsilon, that is again expanded. But sigma D is a conductivity of the dielectric material and tan delta is nothing but sigma D by omega epsilon double dash, which is nothing but the loss tangent. For the low loss dielectric substrate, the major attenuation factor at microwave frequencies arises due to the finite conductivity of the strip conductor. This contributes to the ohmic losses. When the substrate is low loss, the main attenuation is because of what? Because of the strip conductivity losses. So that contributes to the losses due to the current in the strip line. And for simplicity, we assume uniform current distribution in the region between minus W by 2 less than X less than W by 2. The attenuation constant due to the ohmic losses of the white line is given by alpha C using this formula. So alpha C and alpha D we find. Combining both will give me the total attenuation cost in the microstrip line. The commonly used substrate materials for strip and microstrip lines are polytetrafluoroethylene, that is PTFE or Teflon, artiduride, alumina and sapphire, whose electrical characteristics are given. Alumina is most widely used for the frequencies up to 20 gigahertz. At higher frequencies, sapphire can be used. So this table will tell the epsilon R value and loss tangent value of different materials. So when we come to the advantages and disadvantages of this, advantages will be small size and less weight, and can be flash mounted on a metallic body, increased reliability, low cost, easy access of component mounting. Z0 can be controlled by defining the dimensions of the single plane. Passive circuit design is possible easily by changing the dimensions of the line in the one plane only. When we come to disadvantages, low power handling capability due to small size. Since they are very small, the power handling capability will be less, and radiation losses from the open structures like microstrip, strip line and coplanar lines will be more, and this loss can be reduced by confining the field lines more in the dielectric substrate of a high dielectric constant material. By choosing a high dielectric constant dielectric material, you can try to reduce the radiation losses. So with this, I give an introduction to the type of planar transmission lines, and even now when we come to the coplanar and slot line, the mode of propagation is TE. I didn't have any separate explanation for the coplanar and slot line, but both of them, the construction you can explain, and the field distribution is shown here. The mode of propagation in the slot line and coplanar strip line is nothing but it's a TE mode of propagation. So with this, we conclude the planar transmission lines. So thank you.